In this video, we're going to introduce the concept of two sample tests. That's why you see here that this is called a multiple sample inference. It's what happens when you take more than one sample or you want to kind of compare two different groups. So we want to look at two sample tests. Sometimes the whole reason behind comparing two samples is you want to compare two different populations. So things you might want to compare between two populations is you might want to compare things like means or the medians or maybe even the mode or the standard deviation. Maybe you compare the range, etc. So you can think of lots of things that you might want to compare between two populations. So let's compare these sets of, we have different sets of two populations that we want to compare. Now we're just given box plots. For box plots, if you want to look at the center, it would be the median because box plots have a little line for the center. They don't really show you where the mean is, so you can't really compare that. And we might want to compare the spread, and the spread on box plots, probably the easiest thing to do would be the interquartile range. So the IQR is the interquartile range, or it's the difference between the first and third quartiles. Basically, it's the length of the box. Not the whiskers, just the actual box. So that's what you can easily compare visually from a box plot. So when we look at these two populations, let's call this one A and B. Okay, so just looking at them, how do their medians compare? So the median is the line in the middle. It looks like they have the same median. Okay. But the bottom one, the same median, so that would mean same centers. But the bottom one, if you look at the bottom one, it's a lot skinnier, right? So up here, most of my data is in this blue box and is pretty wide, and the red box is pretty skinny. So B is skinnier, so it has a smaller spread. Now again, we said we're just going to kind of compare the interquartile range, which is the width of the actual box, and not the whiskers. When we look at our next one, let's again just call them A and B for ease of reference. It looks like the medians are quite a bit different, or the centers. B is a lot higher, right? All the numbers are a lot higher. So B has a higher center. But if you look at the spread, it seems like they have the same spread, right? They're both the same width, so they have the same spread. See, for my next one, here's A and B again. It looks like A, most of their numbers are a bit higher. The center is certainly higher. So A has higher center. And if we compare the spread, B seems to be a lot skinnier. So B has smaller spread, or it's skinnier. So it definitely has a smaller interquartile range. That also means it would also have a smaller standard deviation, just less spread. Okay, let's see if we look at this one, my last one, A and B. Looks like A has a higher center. The spread is a lot closer on these ones, but it looks like A is still slightly skinnier, so slightly smaller spread. So that's just kind of comparing them visually, and we often want to compare two things just by looking at the box plots. So why would you want to compare two populations? So perhaps you could think of it as people on like experimental treatment A and people on experimental treatment B. So you'd want to compare these two treatments to see which one is better. Or you can think of it as like one population is the result of an old process, maybe the old status or the old drug that everyone's currently taking. And the second population is the result of a new process, so like a new drug they might be trying to introduce. By comparing the two populations, we could see which treatment or process gives us better results. And to do this, we'll go ahead and take samples from each population. First, though, let's talk about some different ways that we can take samples from both populations. Okay. So let's say we want to compare the repair costs of moderately damaged cars at two garages. We want to see if garage 1 charges customers less to repair their cars than garage 2. Okay, there's a few different ways that we can do this. we could take independent samples. And what this is we just randomly select 10 cars to take to garage 1 and get cost estimates for those repairs. And then we'll take 15 different cars to garage 2, get cost estimates for those repairs. But what if the cars that we take to garage 1 just happen to be more severely damaged? Then garage 1 would be cheaper, but they would charge more because more work needs to be done. And so that doesn't seem like it'd be very fair, right? So they just happen to be the worst cars, and so there's more damage, and so garage 1 looks more expensive, even if it might not be. So there is a method that works better, which is called paired samples, or sometimes called matched pairs, depending on which textbook you look at. And so for this one, you could randomly select, say, 10 damaged cars and take each car to both garages. So the repair costs at each garage are obtained for the same cars. So each garage looks at the same car, so you know that you're not changing the cost based on how much damage there is, because each car has the same damage when it goes to each of these garages. Okay, and so that gives you the true difference in the actual cost based on the garage. So these paired samples kind of always would give you better results, but you can't always do that in real life. So sometimes we do use independent samples, and that's really what ends up happening most often. But if you can, paired samples are great. Let's try another example. What if we wanted to compare 2 brands of tires to see which one lasts longer? We could try and take independent samples. So like we could put maybe brand A on 30 cars and brand B on 30 different cars. But what would be the problem here? What are some things that could influence our two groups of cars besides actually the tires? You could have different driving styles, or perhaps the terrain that you're driving over, the mileage of the cars, etc. So there could be a lot of things that could be different between the two groups. Now, if we're just randomly assigning people to each group, we're going to hope that a lot of these differences, just by randomness, kind of cancel each other out and the two groups are fairly similar. But you always have that chance that you just happen to get all the crazy drivers in Group A, or all the people that are going off-roading in Group B. And so you can affect it that way. So if you wanted to try dependent samples instead, or in other words, paired samples, if you wanted to try paired samples instead, what you could do is you could put both types of tires on each car. And then that way you know that each set of tires is going to go to the same place with the same driver, with the same mileage. And so the difference in the results will be due just to the types of tires. What if you wanted to test 2 new drugs on patients? Well, if we tried independent samples, we'd test, say, 40 patients on drug A, 50 patients on drug B, and compare the results. Now notice here that I'm not making sure that my number of patients is the same in each group, and that's okay. Really, in practice, lots of times you have slightly different numbers in each group just due to various reasons. Okay, but what if, say, like all the patients on drug A happen to be older, so they don't really respond to the drug as well? Then drug B would seem to work better, but drug A might actually be better. Well, what if we try to give each patient both drugs? Well, we don't usually want to use this method because the 2 drugs could interact and then we still don't get valid results. Or they might not just interact, maybe you'd end up overdosing them or something. That would certainly be bad. So what can we do? This is where we do something like, what we're going to do is we're going to try to match people up by things like height, weight, age, health, gender, etc. So basically, we're trying to create almost identical pairs. Now, of course, no 2 people are exactly alike, so you're just trying to get people that are as similar as you possibly can. And then we can randomly assign one person from each pair to each of the drugs. And that way, each of the 2 groups should be fairly similar. So this is what we do if we can't truly do paired samples. And again, even this is sometimes too much work and you just end up with independent samples, which is still okay. Just keep in mind, if you have a choice, this would be better. So let's go ahead and try a hypothesis test for paired samples. So back to our garage example, we wanted to go compare the price of the two garages. So someone actually did this. They took a sample of 7 damaged cars, and they took them to garage 1, and you can see all the repair costs, and then you can see garage 2, their repair costs. Okay. And these are in hundreds of dollars, so that's $710, $900, $1,100. And so they take each car to each garage, give the answers. Now let's remind ourselves, going back several pages, that I want to know, is garage 1 cheaper than garage 2? So that's just what it said on the first page. You probably forgot, but that was our suspicion, is garage 1 cheaper. So you'll notice here in my table I have each of the 7 cars, the repair costs, and then I'm going to ask you for the paired differences. So since we want to compare the two, it makes sense to see what the difference is for each car. So what we're going to do is we can do garage 1 minus garage 2. Now, I didn't have to put them in this order, I just did because garage 1 came first, but once I write it in this order, I have to keep this order for the rest of the problem. So you can pick the order you write it down for first, but then you have to keep this order. Okay, so we think garage 1, or we're trying to do garage 1 minus garage 2. So we'll do 7.1 minus 0.9, or 7.9. So this gives me a difference of negative 0.8. And 9 minus 10.1 gives me negative 1.1. 11 minus 12.2 is negative 1.2. 0.1, negative 0.5, negative 0.7, and negative 1.4. So notice I now have 7 differences. So what I can do is I can look at these differences as just one sample. So the differences are basically a sample on their own. So I can look at the box plot of the differences. It looks almost symmetric. I can look at a normal quantile plot of the differences, and it's almost symmetric. That's close enough. Okay. I can even do descriptive statistics on it. I can do my count, so n equals 7, my mean, x bar equals negative 0.8, and the sample standard deviation of s equals 0.503. Okay, so you can even go through and find all of these results for the differences. Now, because it's the differences, sometimes we'll put a little d on here just to remind ourselves that we are talking about the differences themselves. Not completely necessary, just kind of helps us remember that we're talking about the differences. Let's see, so we want to know if there's a difference in the true population mean repair cost between the two garages. Because we have paired samples and we found the difference for each pair, we really only have one sample, i.e. this is our one sample. So really we don't have 2 samples, we just have one sample. So we don't need a new test, instead we'll just use our one sample t-test on our paired differences. So t equals x bar minus the mean over s over the square root of our sample size. Notice this is exactly the same as our normal t-test statistics, see, like exactly the same. But we just put d's on to remind ourselves that it was for differences. Kind of pointless because it's, again, the exact same test. So this really isn't anything too new for this test. Okay, something that is new though is you have to kind of pay attention to what numbers you put in where and which direction you do your sign. Let me emphasize. So, because what is this mu? Okay. So let's come back up. If we're doing garage 1 minus garage 2 and we're looking at the differences, if your two means were equal, then what would be the difference, or what would be the mean of the differences? Okay. Let's see. So if the garages are the same, so if your two garages are equal, or really their repair costs are about the same, then the mean of the differences would be equal to 0, right? Does that make sense? So if the two garages were equal, all of these numbers would be like about 0, close to 0. If we found the average, it should be about 0. Let's see. And if garage 1 is cheaper, then the mean of the differences should be what? Okay. So if garage 1 is cheaper, all of these numbers should be less than the numbers at garage 2. And so when you subtract them, you're going to have small numbers minus big numbers, and you're going to get a lot of negatives, kind of like what we got here. We'd expect this difference to be less than 0. And so if you're doing paired differences, this mean is always kind of going to be 0, or at least usually 0. Occasionally, you might have a more complicated problem, which we'll get to later, but for the most case, it's going to be 0. So usually this mean is 0, so they don't even bother writing minus 0, and they just do the mean over standard deviation over square root of sample size. So let's come down here. We want to conduct an appropriate hypothesis test to determine if garage 1 charge is less than garage 2. So we're looking for garage 1 less than garage 2. So our hypothesis test, our null hypothesis test, well, we want null and alternative hypotheses. Okay. The null would kind of always be status quo. That would be that they'd be equal to each other. So this would give us that the mean of our differences is equal to 0. The alternative, the hard part is you have to figure out which sign to do. But if you wrote garage 1 less than garage 2 and you kept your same order every single time, so if you did garage 1 minus garage 2, and you write garage 1 minus garage 2, and you always put garage 1 first, then you can just use the same sign. And it'll be a less than, because you keep the same order. Let's see, so we did our hypotheses. You need to know alpha. Let's just use 0.05. You need to check your assumptions, which our data, we looked and it seemed fairly normal, which is good because it was a small sample size. You need your test statistic, which again in our case is going to be the mean, our sample mean, minus our hypothesized mean, over standard deviation over square root of the sample size. And again, you can put these on. It really just makes it look cluttered. You're welcome to just leave those off. And for this, now we come back up to our data. So our sample mean was negative 0.8, standard deviation 0.503, sample size 7. So negative 0.8. Our hypothesized mean is that there's no difference. The null hypothesis is that they're the same, so the difference would be 0. And S is 0.503 and square root of 7. So we get negative 4.207 as our test statistic. Now for a t-test, so this is basically just a t-test, you need degrees of freedom. Degrees of freedom are n minus 1. So degrees of freedom is n minus 1, so n was 7, 7 minus 1 is 6. So my p-value, here's my negative 4.207. Now notice we're looking for a less than, so we're looking for the area to the left. So we open up our t-table. We're looking for 6 degrees of freedom, and we're looking for the number 4 point something, so that would be about here. Now we're using symmetry and looking for a positive value. So we're between 0.001 and 0.005. It's 0.001 to 0.005. So my p-value is somewhere between 0.001 to 0.005. So that would be a small p-value, certainly smaller than alpha equals 0.05. And so we'll reject our null. And we have basically evidence that the mean of the differences was less than 0. Or we can say that we found evidence that the population, so remember this is all that garage 1 is less than garage 2, so the population mean cost at garage 1 is cheaper than at garage 2. So let's try another example. Some people think mental patients are influenced by the moon. We want to conduct a study of dementia patients in nursing homes. For each patient, we counted the average number of disruptive behaviors on days with a full moon and also the average number of disruptive behaviors on days without a full moon. Conduct a hypothesis test to determine if there's more behaviors on days with a full moon. So I gave you this nice table, so for each patient you can see the moon days, their other days, and the difference. So just looking at these numbers, 3.33 minus 0.27 gives me 3.06. So it looks like they're doing moon minus other. So it's important to know the order that you're subtracting in. So moon minus other. Because now you need to keep the same order for everything else. Because now we want to see, do we think that the mean for the moon, how do you think that would compare to the mean for other? Okay, so we're hoping to see, let's see, mental patients are influenced. We want to see if there's more behaviors on days with a full moon. So we want the moon to be bigger. Okay, so make sure you always keep the same order. If they subtract a moon minus other, then you want to compare the means in that same order. Okay, and now that would mean the mean for the differences would be, if this is a greater than, then this would be greater than 0. You keep the same sign as long as you write everything in order. Okay. So these are the actual differences. So this is our one sample, so we're just doing basically a one sample t-test. It looks like it's normal enough. It's not great, but it's normal enough. Remember, we only care about it if it's really not normal. And our statistics over here, looks like I have sample size of 15. My sample mean is 2.4327. And my sample standard deviation is the 1.4603. Now again, we're just putting these on here to remind ourselves that we're talking about differences. They serve absolutely no purpose. It's just exactly the same as a normal one sample t-test. Okay, basically just, it's a t-test. Okay, so for a t-test, you do things like choose alpha. I'm going to just choose 0.01, just so we have practice working with something else. Okay. Let's see, we also need to check, we checked and saw that it was normal. We need our hypotheses. The null hypothesis would always be that your two means are equal, and so then our difference would be equal to 0. And the alternative, then up here we said that we think that the moon has more disruptive behavior, so the mean of the differences should be greater than 0. Okay, you need your test statistic, which is just like a t-test statistic. It's just x minus the mean of the differences over s over the square root of n. Now again, if you want, you can put little d's here to remind yourself what you're doing, but it's not really necessary. Okay. So the sample mean over here is the 2.4327. Our hypothesized mean in the null hypothesis is that it's just 0, that there's no difference. Standard deviation is 1.4603, and square root of 15. So this gives me 6.45. You also need degrees of freedom, which for t-test is just n minus 1. So 15 minus 1 gives me 14. For your p-value, because this is a greater than alternative, we want the area in the right tail. So here's my 6.45, and we want the area to the right. So t-table, 14 degrees of freedom. We're looking for the number 6 point something, so that's way off here. So my p-value is smaller than 0.0005. So this will be less than 0.0005. So my p-value is less than 0.0005. So really, no matter what alpha is, that's a very small p-value, but it is smaller than our specific alpha of 0.01. So we'd say it's a small p-value. And we need to reject the null. And if you do that, then you have evidence for the alternative. Our alternative being that our mean of the differences is greater than 0. And then what did that mean for us? So if our mean of our differences was greater than 0, then that means that the mean for the moon is higher than the mean on other days. Okay, and so we write something like, we found evidence that the average for all the mental patients is higher on days with a full moon.